Welcome to Data Mining, Lecture 6, Part 3. This part will conclude text mining. In this part, we will focus on two types of text mining, namely the trend discovery and the event discovery. What is trend discovery? For example, the occurrence of the word Java in recent articles on computers might suggest either an upward or downward trend in the popularity of the Java programming language. So a trend might be recognized in a document collection by detecting sudden changes in the frequency of certain noun phrases over a period of time. Okay, so for example, if we digitize all these newspapers, in fact, most of these newspapers right now are on the web in digital form. So we can scan these newspapers or magazines, and if we see sudden changes in the frequency of some noun phrases, we are able to detect either uptrend or downtrend, at that time. So that's a basic idea of trend discovery. And as you can imagine, to do the trend discovery, we need to borrow a lot of string searching and string matching algorithms, because this is to basically scan strings, which are texts, and then to find the changes in the frequencies of the strings. To discover trends in collection of texts, consider, please pass on this to those people, to the late students. Consider a set of words W, phrases P, and text fields F. Give me back. Give me back. If you have questions on this grading of the homeworks and so on, you should check the grader. And if you don't know who the grader is, you can raise the questions, and I will post the email of the grader so that you can send email, make appointment with the grader, and to check your grades and so on. Homeworks are very important, as I emphasized many times. And the basic philosophy is that you would rather hand in something than nothing. Okay, if you hand in something, there's greater grades, and then you get a grade. If you hand in nothing and you pass the due date, according to the policy, you are not able to hand in anymore. Now for that case, you get 0 for that item. And all the points are accumulated. So if you have 2 or 3 zeros, that hurts your grade a lot. Okay, and all the points eventually are accumulated using my program, and then will automatically generate a final grade for you. And that is true also for distant learning students and for face-to-face students. So all the homeworks are very important, and all the implementation projects are also very important. They are counted toward your final grade. So we consider a set of words W1 through Wn, and these are keywords. And they can so each word Wi can be represented by the parenthesis Wi. And also we also consider a set of phrases when we do the trend discovery. So you have a set of phrases P1 through Pn, where each phrase is represented by a sequence of keywords. Notice that here we use the sequence of keywords, and we use the notation parentheses. So that means the order among the keywords is important. So for example, a phrase data mining is different from a phrase mining data. Okay? And then we sometimes represent a phrase by this notation, bracket and keywords and so on. And then we also consider a bunch of text fields. So text fields F, and this F is equal to F1 through Fm. And what does each Fi represent? Each Fi basically is a collection of keywords plus a collection of phrases. So if you look at this, you can see that these Wi's represent keywords, these Pi's represent phrases, and these Fi's represent paragraphs. Okay, and for each paragraph or text field, you pick up important keywords and important phrases to represent that particular paragraph. So these are basic ideas, definitions when we try to do the trend discovery. And then now you are given a set of text documents T1 through Tn, and each document has a timestamp that represents when this document is registered into the database. And also, that document has a bunch of paragraphs or text fields, F1 through Fm. So F1 is a paragraph, the first paragraph, second paragraph, and so on. And each paragraph Fi has a bunch of keywords and also a bunch of noun phrases. So to capture the notion of phrases for a more complex structure, we sometimes use the notion of K-phrase. Okay? A one phrase is a list of elements where each element is itself a phrase. For example, this is a one phrase. Okay? In this phrase, you have two keywords, data and mining. And then, and this is another phrase, okay? And this data mining and a book appear in a single paragraph. So we use a bracket to contain these two phrases. On the other hand, for a two phrase, we use this notation. So you have web mining, and that's a one phrase. And book is another phrase. And you have a bracket, okay? And that basically gives you a paragraph, okay? And then you have another paragraph. And you put these two together, and for that we call this a two phrase, okay? So in this example, web mining and a book occur in paragraph 1, and data mining occur in paragraph 2. And they occur in different paragraphs. So we refer to this as a two phrase, okay? You have phrases, but they are not in the same paragraphs, okay? But these are notations. The idea for trend discovery is to identify frequent phrases. Given a bunch of documents, so there are several definitions for frequent phrases. One definition is that for the same document, for the same book, you try to identify phrases that occur very frequently in this book. For example, Jordan. Jordan might occur frequently in Sports Illustrated. Okay? Or Michael Jordan, that's a phrase, right? Michael is a keyword. Jordan is a keyword. A more interesting discovery algorithm is to find frequent phrases across different documents. So you have one newspaper here, and you have another newspaper, and you have another newspaper, and so on. You try to discover frequent phrases that occur in all these newspapers, and those phrases represent a trend for the current situation. Today's newspaper talks about Michael Jordan. Tomorrow's newspaper also talks about Michael Jordan. So that means Michael Jordan is to come back to the basketball court again. So that that we detect that particular trend. Another trend discovery algorithm is to try to generate histories of phrases. Another type of trend discovery algorithm is to try to find patterns that match a specified trend. you have a particular query or trend which is composed of a bunch of phrases. And based on this, you try to search the text database to see whether this text database, whether these documents at hand contain this particular trend or not. Now, if you look at these algorithms, all these algorithms are concerned with string discovery or string matching or substring matching and so on. So, there are several algorithms. Now, instead of talking about these algorithms in detail, I would like to draw your attention to a particular paper we published in 1994 in the Sycamore conference, and later on we modified that paper slightly and applied to the biological domain and published in the nucleic acids research. And that paper is posted on my website in 1994, nucleic acids research. We are going to talk about that paper a little bit at the end of the semester when we talk about bioinformatics data mining. But the idea is that paper is to do the following. Given a set of strings or a set of newspapers, whichever you want, okay? We basically represent these documents using a suffix tree data structure, which is a very common data structure in string searching. And then we are able to discover frequently occurring strings in this set of strings. So, given a set of strings, or a set of protein sequences, or a set of DNA sequences, normally a set of protein sequences, our algorithm is able to discover frequently occurring subsequences, also known as motifs, in this protein set, okay, or protein sequence set. So we can apply that type of algorithms directly to detect trends here in newspapers, because newspapers are strings. Look at any newspaper or any book, right? Then you start from the beginning. There are actually a bunch of paragraphs where each paragraph is a bunch of strings. Each sentence is a string. So you can use, for example, our tool to discover frequently occurring substrings in this particular string database. And that's basically is to identify frequent phrases. And we make that software available in public. That software is called S-Discover. Yesterday there was a student from La Trobe University in Australia. La Trobe University, and he was asking me to send him the software which we call S-Discover, String Discover. And I sent him the software. He was saying that he wants to use the software to do some kind of trend discovery in newspapers. So if you are interested in this, please feel free to ask me, and I will send the program, and you can play with the program. And that program basically is to accept a set of strings where a string could be a protein sequence or a string could be a paragraph of sentences, and then automatically discover frequently occurring subsequences in this set of sequences. And that program is very powerful. And we published that algorithm in 1994 Sycamore conference, and then that has a lot of impact. In fact, that paper was, among all my 100 publications, was the one that cited the most frequently. So that indicates the impact of that paper. Okay, the paper title is Pattern Discovery in Scientific Data. But in fact, we focus on the protein sequences when we talk about scientific data. Okay, and they are sequences. And we pioneered the idea of using this suffix tree to do the sequence discovery or sequence searching. And after that, there are other professors, Jeff Vitter, for example, from Duke University, applying similar ideas. And then later on, as the paper you are reading, Zhang Hui, the Bell Lab people, division, so on, they apply suffix trees to try to discover query matches in XML documents. Okay, so people then apply these ideas in many places. So I encourage you to look at this paper, and also if you want to, not for this course project, but if you want to dig into that in your master project, you can play with that software program. That software program was developed by my first PhD student, Gongwei Chen, and that program is very robust, very good program. Okay. Now look at the third trend discovery algorithm. This basically is a pattern matching program. You are given a trend, which is a set of strings or some strings, several noun phrases, and you try to search your string database, trying to find the patterns that match this trend. And this again is a stream matching program, okay, stream matching type of algorithm. And I think in March or sometime around that, I'm going to post my post-survey paper on the website. And please feel free to download that paper, and you will find a lot of relevant papers about stream matching and the tree matching with applications to XML, web databases, and the data mining, and so on. Okay, we basically survey all the published papers in this field, and we find a lot of stream matching algorithms and pattern matching algorithms applied to this trend discovery, data mining, XML, query processing, and so on. That's a very interesting field. The next text mining task is event detection. Event detection in the context of news is the identification of stories in continuous news streams that correspond to new or previously unidentified events. Okay? News event detection consists of two tasks: retrospective detection and online detection. And I'm going to give you one algorithm for each task. I'm going to give you one algorithm for retrospective detection and one algorithm for online detection. Now, if you look at these algorithms, you see that they are very much relevant to clustering algorithms. They are very similar. Okay, but then people apply clustering algorithms to event detection. What is retrospective detection? In essence, retrospective detection is to discover previously unidentified events in a cumulative news collection. So you have a bunch of news at your hand where each news is nothing but a string, right? You look at the news. Michael Jordan is coming back, the basketball court, and so on. That's a string, okay? But you can interpret that semantically, then you know that that's that story, okay? And then tomorrow there is another story concerning with the same event. Michael Jordan is coming back to the basketball court, okay? And then they describe another relevant story. So one event contains a bunch of stories where each story is nothing but a string, okay? So you have a lot of stories correspond to one particular event. And then suppose you have a collection or a database of such strings or events, and then you try to use, for example, the retrospective detection algorithm to find a particular event in your database. Okay, so this is something like static discovery. Everything is there. You just try to find something inside your database. By contrast, online detection is a process of identifying new events in real time from live news feeds. You keep on listening to the news from the television or from the radio, and then you apply the algorithm. The algorithm will detect new events in real time. Okay, so that's online processing. So the algorithms will be different because one is static, one is dynamic. One is to look at the static database. Everything is there. You just apply the algorithms to do detection. And on the other hand, for online detection, you keep on listening new news, and your algorithm will run. Will try to discover there's new events. Where an event is nothing but a string, by the way. Okay, that's what we do. That's basically about stream matching. Both processes assumed to have no knowledge of the nature of the news stories, but do have access to unprocessed historical news stories in chronological order, which they use as contrast sets. Okay, for both online detection algorithms and the retrospective detection algorithms, what you have is you have a collection of existing events or stories. You have them there. For the retrospective detection, your job is just to discover events inside that database. That's all. For online detection, what you do is you get the new news and you compare with the existing news or those existing classes of stories, and then you try to make decisions. Okay? So news event detection is a discovery problem that mines data streams for undiscovered patterns in news story content. News stories occur continuously, tending to come in bursts called news bursts. News bursts can be pictorially illustrated using a temporal histogram where the x-axis is time representing from day 1 to day 365, from the first day of the year to the end of the year. And the y-axis is the story count per day. For that particular day, how many stories are relevant to that particular event. Okay? So for example, here is a temporal histograms of 2 fictitious news events. So look at this. So this shows that at this particular day, for example, day 10, you have 10 stories relevant to event 1, and so on and so on. This is true in real life, right? When Michael Jordan is coming back to the basketball court, suddenly, almost every day, you hear the news stories talking about that particular event. Today, you hear that people are analyzing his salary, and tomorrow people are analyzing whether he still has that skill or not. And the third day, people are analyzing whether, how good he will be, and so on and so on. And after a while, that event is of no interest anymore, and people are interested in another event, and so on. And then you have event 2, and then the first day, so many stories from so many newspapers are concerned with that particular event. Okay, every newspaper is reporting different stories written by different authors relevant to that particular event, and so on and so on. And that's true for in our real life. Okay, if you look at the television news broadcasting, you see that this is very, very typical in our life. So the temporal histogram illustrates 4 key observations. First, news stories related to the same event tend to be temporally close. Okay, in these particular days, everybody is talking about this particular event. So many news stories are published talking about this particular event. Okay, and they are close together in this week or perhaps in this month. Okay, but after this month, people's attention might be shift to another new event. Okay. Second, different events are usually separated by a time gap between 2 news bursts. Third, a shift in vocabulary and changes in term frequency distribution are very typical of a news event. In these days, people are talking about Michael Jordan, sports, and then compare him with Kobe Bryant. So, and then at that particular time, people are talking about different things, and so on. Okay. So the vocabularies are changed. The vocabulary will change, and then terms will be changed for different events. Events tend to be reported within a brief time window of 1 to 4 weeks. So now you have this notion of window. Okay. So these characteristics are taken into consideration when we design event detection algorithms. And actually, most of these event detection algorithms are based on clustering methods, as you will see in our next example. This is a retrospective event detection algorithm. What we do is first we sort the stories chronologically into a list. This story is published in 1999, September, and then October, Another story is published in year 2000, January, and so on. You sort the stories chronologically. And then you take the earliest story off the list and compute the cosine similarity of this story with all the existing clusters you have. Okay? Now, here, once again, we model a particular story by a vector. That is, you look at the keywords in that story, and then you can model that story as a vector. I have already repeated this many, many times. You can always model a document by a vector, okay? By a vector of keywords. A story is nothing but a document. Look at the newspaper, a particular story. That's a document. That's a particular document. That's a story. Okay, so you calculate the cosine similarity of this story with all the existing clusters. Okay, now we have learned how to calculate the similarity between 2 documents. But then how to calculate the similarity between one document with a cluster? Well, what you can do is you calculate the similarity between this document with each document in this cluster. And then you can take the maximum or minimum as the similarity between this document and this cluster. You can always find some formulas to do that calculation. Is that clear to you? So you have several clusters of stories where each cluster might represent an event. Now you have a bunch of stories sorted, okay, chronologically there, based on the years or time they publish, all right? You take the first story, and that story can be modeled by vector, right? You all know that. Each document can be modeled by vector. And then you calculate the similarity between this vector with all the existing clusters to see which cluster is closest to this vector or story. If the highest similarity score is above a threshold, then this story is added to that cluster that is closest to this story, okay? And then the prototype vector for that cluster is updated, because after you add this story to that cluster, the prototype vector, which is a representative vector for that cluster, has to be updated to include some keywords in this new story. All right? However, if you observe that the similarity between this story and the existing clusters is too low, that perhaps means that this story is nothing to do with any existing cluster of events. For that case, you create a new cluster and then you put this story in that new cluster, because this new story, the story might belong to a new event. Okay? And you keep on doing so for each story in your list until you finish clustering them. That's what we mean by retrospective event detection. Okay? You look at everything, every story, all the stories are there. And then you have different clusters of events that represent previous events. And then you try to assign each story to one of the clusters. Or perhaps if none of the clusters is relevant to this event, you put this, this might be a new trend. So you put that story in a new cluster. Okay? Probably that represents a new event. Any question about this algorithm? So this actually is very similar to clustering algorithm. All right. Any question? That's a static event detection algorithm. Let us look at online detection algorithm. Now, once again, you have a bunch of clusters of events. Each cluster contains stories relevant to a particular event, and you have a bunch of clusters there. Okay. Now, and you have a window size. That's the number of clusters of interest that will be kept in a database. Remember, an event might last 1 to 4 weeks, and after 4 weeks, nobody is interested in that event anymore, and therefore, the cluster corresponding to that event might be removed from your consideration. So you keep a window size. The window size, okay, represents the number of clusters of events you are interested in. Okay? And the online news event detection algorithm processes stories from a news stream, one at a time as they arrive. You keep on listening to radio or you keep on watching the television, you see the new events, okay? New stories. And then you try to assign that story to one of the existing classes. You try to see whether that new story is relevant to any existing events or not. One cluster corresponds to one existing event. Is that clear? So you have a bunch of events there. Now you keep on listening listen to new stories, new news, okay? And the algorithm will tell you yes or no, okay? Based on some similarity measures with respect to previously processed news event clusters, okay? And there are several threshold values for this algorithm. Detection threshold, TD, that specifies the minimum similarity score required for the system to be confident that the current story belongs to an old event. Okay, you have a bunch of old events there, where each event corresponds to a cluster of stories relevant to that event. So suppose right now you have 5 events, okay? And each event has a cluster of stories. Is that clear? Now, so what is the clustering threshold? That specifies the minimum similarity score required for the system to be willing to add the current story at hand as a new member to an existing cluster. So if the similarity between this new story and this existing cluster is large enough, meaning that they are close to each other enough, then, and their similarity is greater than or equal to this threshold TC, and then you assign this new story to that existing cluster. All right? Otherwise, you should create a new cluster for this news, okay? Because that might be concerned with a new event, okay? Window size TW, that specifies the maximum number of clusters or other aging limits available to compare the current story with. At each time, my window size is 5, meaning that I only keep 5 most interesting and the most recent events, where each event has a cluster of stories. So I only keep 5. As we pointed out in the previous transparency, after a few days, after 1 to 4 weeks, interest might be shifted to other new events, and therefore you might want to remove one cluster from your collection and add another new cluster to your, to your consideration. Is that clear to you? That's why we always keep a window size that represents the number of events or the number of clusters under consideration. Normally, the clustering threshold is greater than or equal to the detection threshold, but for our illustration purposes, let me assume that these two actually are the same. Okay? So let us see how the algorithm works. You start with a set of clusters K and the predetermined values for TD, TC, and TW. Okay? So you have a bunch of clusters. And suppose your window size is 5. So the number of clusters must be less than or equal to 5, meaning that you, at any moment you are only interested in 5 events or 5 clusters. All right? Okay. And these are predetermined. Okay. So the algorithm is pretty simple because you have so many predetermined values. Okay. So in many times perhaps you have to tune these parameter values at the runtime. Then second step, you're reading a story as current. So that's a current story. You're reading radio or you read newspaper. But you watch the television. Now you see a new story, a news. So that is a current, and you compute its similarities scores with the existing clusters. Okay. So you compute the similarity between this new story with the 5 existing clusters to see whether this story is similar enough or close enough to one of the existing clusters. Suppose you have 5 clusters and you have a new story. You compute the similarity between this story with this cluster and with this cluster and so and so on. And you identify that cluster 3 is most similar to this story. All right? And the similarity value is S3, for example. We use SM to represent general cases. Then you have to make sure that this similarity, they are similar enough, fine. But we have to make sure that that similarity is greater than or equal to the predetermined threshold, meaning that they should be close enough. All right? So you have 5 clusters. You compute the similarity between this new story with the 5 clusters. Among the 5 clusters, you identify that this cluster is closest to this story. So they are likely to be relevant. After that, you have to double verify. So you look at the similarity value, you compare that similarity value with the threshold TC, for example, or TD. If the similarity is greater than or equal to the threshold TD, then we know that the current story actually is relevant to that particular cluster, and also that the event associated with that cluster, and therefore this story is an old event. So you output the output this is an old event. It's not a new event. So that's what you output, all right? Because they are so similar to each other. On the other hand, if the closest cluster is still far away from this current story, that is, their similarity values is less than the threshold TD, then we know that this story, this is a new event. So we output, yes, that's a new event. All right? And furthermore, we look at that similarity value, because if that's greater than equal, if that similarity value is greater than equal to the threshold TC, that means it is so close to the existing cluster. So I add this current story to that particular cluster and update the prototype vector for that cluster. On the other hand, if the similarity is less than the threshold, then I create a new cluster and I put the current story in a new cluster, because that new story is relevant to a new event, nothing to do with the current events. Okay? And now, as you are processing new stories or new stories or new news, at one point you might have more clusters than the specified window size. In other words, the number of clusters might be 6, and your specified window size is 5 only. For that case, you have to remove the oldest cluster. You only maintain 5 most interesting and the most recent events in your window. All right? When you have new stories or new clusters inserted, and when you have more such clusters, at one point you have to remove the old uninteresting cluster from your window, and you repeat these steps until there's no more input, and that's how you do the online event detection for the text mining. So any question about this algorithm? So that's a very simple algorithm. The only tricky part is how you calculate the similarity between a new story with the existing stories in those clusters. Okay? I already gave you a hint. You can model a story as a vector, The story is a document, right? You can model that document as a vector. And you can use a cosine similarity to do that calculation. But as I point out, cosine similarity is just a fundamental thing, not necessarily the best. So when you deal with real life event detection, you might want to invent new similarity measures and use that to calculate the similarity between a story, with a cluster of stories. Okay. For example, you might want to identify the occurrences of some hot keywords and use those hot keywords, to determine the similarities and so on. So these are all domain dependent, and these have to be modified when you actually apply this algorithm to the real life. And by the way, this algorithm is actually being implemented in many newspaper or television data mining systems. Okay, people use these tools to detect new events. Now, and to analyze the events. Now, of course, when you read newspapers, you can observe what events are most interesting recently. Okay, but this algorithm can actually automatically detect those events, and then you can verify them with your newspaper studying, and you can see whether they are consistent or not. So this is a very powerful program and very powerful tool. Okay. Any question about this? Yes, louder, please.
Yeah, I want to know if there are any possibility that a new story belongs to 2 clusters or more. I mean, it's similar to class 1 and similar to class 2. Is there this kind of possibility?
If you look at our algorithm, we take the similarity SM to be the maximum of all the similarities between this new story with the existing cluster. So we take the maximum value. That could happen only if you have two clusters that have the same similarity values with this new story, right? So they both have, for example, similarity 10, and they are both closest to the new story. For that case, how you're going to deal with that? So there are several strategies. One strategy to break the tie is that you randomly choose one cluster and try to do the clustering. Second strategy is that you redevelop a new similarity values and then try to look at these two clusters and use that similarity value, as a new way to try to identify the closest clusters based on that new similarity value. So you have several strategies to break a tie. The third strategy is that perhaps then you look at this new story. Why this new story is close to two clusters? Is that because your clusters are not distinguishable from each other, or is that because the stories has descriptions overlapped with the descriptions of both events and so on? So you have to look at the situation and see what happens. For example, normally, if this story talks about Michael Jordan, this story will not be concerned with, for example, September 11th event, because they are so different. So why your story is relevant to two events? Okay, so we have to re-examine these events or these clusters or the prototype vectors for each cluster. A prototype vector for a cluster contains representative keywords, those keywords that occur most frequently in that cluster, and you have to re-examine those vectors and so on. Okay? By the way, when we do clustering or classification, it's not unusual that you see a tie situation. So we either want to break the tie, or perhaps we don't care. We just pick up both clusters and we assign this story to both clusters. Okay, there are many different scenarios. If you look at the Swiss Pro site, in fact, one protein might belong to several different clusters. So they put this object in this separate cluster because it is so close to so many clusters, so they put that in multiple clusters. That's one strategy. The second strategy is that you have two clusters that are close to this one. So I just randomly pick up one cluster and assign this to that cluster. This random assignment strategy is not good because you ignore the fact that this object is close to another cluster as well. The third strategy is that perhaps this algorithm is not good. So the algorithm just output the value not determined, or try other choices and so on. Because the algorithm is no good, right? So you have to try another similarity measure or try another algorithm to try to do the clustering or classification. That's how we do when we deal with real-life clustering. Yeah. You have several different strategies to break a tie when you deal with classification. Right, nearest neighbor classifier. If this object is close to 2 or 3 classes, where you should assign this object to? If this object is close to 3 classes, for example, so there's a tie among the 3 classes, you need to find a strategy to break the tie. So that basically that concludes this materials, and then we will just dismiss here.